All right, so yesterday we finished our discussion on ionic bonds and then hopped right into covalent bonds. Again, what is the main difference between, or there's a couple differences between covalent and ionic, but what is one of them? What is the difference between ionic and covalent? How about this? Ionic bonds are between what type of elements? Metals and nonmetals. Very good. What about covalent? What type of elements are they? Nonmetals. Very good. And ionic bonds formed by opposite charges between metals and nonmetals and their ions, whereas covalent compounds, they form in order to satisfy the octet rule. They share their valence electrons with other atoms in order to have a full 8 electrons when possible, with the exception of hydrogen, because hydrogen can only fill the s orbital, which holds 2 electrons. Now, when we have a covalent bond occur, they might be nice to each other by allowing another atom to share electrons with another atom, but sometimes they're just not shared equally. And so if we look at this example, or these two examples between the fluorine compound F2, it's a Brinkelhoff, so it can form a diatomic, and the compound hydrogen fluoride, or fluoric acid. If you notice here in this image, we have a nice, appearing to be evenly distributed pole or shape on the image on the left. What this image is showing us is a distribution of electrons. And so when you have a nice even shape like that, that means you're equally sharing electrons. You have an equal pull. Okay? That'd be like if you are pulling against yourself in tug of war. Okay? You're equally matched. You're not going to really have any change in that rope. Now, when you get to a situation like hydrogen fluorine, you see it is not even. It almost resembles an egg. Okay? Fluorine has a much stronger pull on the electrons than hydrogen does. And so, when it does that, you tend to have a congregation of more electrons closer to fluorine, which in turn causes there to be a higher density or a more negative charge kind of leaning towards this way. Okay, so that would be equivalent to you playing tug of war with against three other people. Okay, so there's an uneven distribution or uneven density between electrons, and that's where we get the electronegativity. Okay, remember this term? Yeah, I believe it was a trend, correct? Well, again, to remind you, electronegativity is the ability of atoms in a molecule to attract electrons to themselves. So in terms of the trends, electronegativity is going to increase from left to right and from bottom to top. All right, that's what the image you have. Okay, you notice on those images for each element you have values. Well, just like with the trend, with some of the trends that we saw in chapter 7, trends are great to have, but they can have limitations. And we're going to see some of those limitations today. In this example here, we're talking about bond polarity, right? So we have, in our practice exercise, we need to determine which bond between certain groupings is more polar. And when we say which is more polar, what we're referring to is who would have a stronger or a larger difference between electronegativities. Okay? And In some instances, we can use the trend. In other instances, we got to use this table. Okay? So here we have boron and chlorine. And the other one is carbon and chlorine. So between these two, what do we see? Something that stands out between these two compounds. They both have chlorine, which is good. They have a common factor. So all we really have to do is look at boron and carbon. Okay? Now, according to the trend of electronegativity, which element, boron or carbon, would have a smaller electronegativity? Boron, why? Bingo. Boron is to the left on the periodic table. Therefore, it should have a smaller electronegativity. So if you were to think about that, again, these two have chlorines together. Which one would have the greater difference between their electronegativity values? What do you think? If chlorine, these two chlorines are going to have the same value in electronegativity, and you said boron should have a smaller electronegativity value based upon its position on the periodic table, which one would you say would have a larger difference in electronegativity, therefore a great or more polar situation? Boron and chlorine. Imagine this. Again, I'm just making up different imaginary numbers here. Let's say chlorine has a value of 10. It doesn't, but we're playing. And boron has a value of 6, and carbon has a value of 7. They're different. Boron and carbon, get it right sometime, are different because boron is to the left, therefore it's going to be smaller. If I were to mathematically solve for this, which one would have the larger result? The boron and chlorine. Okay? It would have a larger electronegativity difference, therefore more polar situation. So that's why boron and chlorine would have a more polar bond. Now what about the next one? Phosphorus and fluorine, or phosphorus and chlorine. Again, what do we see between them? What do we see between them? There we go, phosphorus. Okay, so then we can shift our focus over to the other two elements, fluorine and chlorine. Based upon the trend of electronegativity, who would have the larger difference in electronegativity? Perfect. Phosphorus and fluorine. Fluorine is higher up the group of halogens. And based upon the trend, the higher you go, the more electronegative you are. So phosphorus and fluorine would have a larger electronegativity difference in their values. Therefore, it would be more polar. But what happens if we get into a situation like this, where we have SCl, SBr, SECl, and SEBr? We are to look at these four bonds and try to determine which one is the most polar. So if you look here on the periodic table, you got sulfur here, selenium here, chlorine here, bromine here. This is one of those situations to where it's very difficult to try to use the trend to solve this question. This is a situation where you'd have to refer to that table that you received as you entered the room to solve. That's what I want you to do right now. I want you to use the values on the table to help determine which one of these four compounds has the largest electronegativity difference. So go ahead and do that. Spend about a minute on there or so. And don't worry about if your answer is a plus or minus. It doesn't matter. Okay, it's all about difference. Listen, what do you think? Oh, I saw you writing them down. You want to phone a friend? Yeah. Phone a friend. Who's going to answer your call, Alyssa? Bingo. Now, since you answered it, do you have all the numbers written down? Okay. So let's start with SCl. What do you have as a difference? Okay, for SBr. SEBR? SECl. So yeah, because the difference in electronegativities is larger in SECl, it will be more polar in that situation. Now, if you're trying to work this out by comparing lights, comparing these compounds one at a time with another and crossing off, eliminating some, it's a very thin margin because the values between these four elements can be very close together, and it may not actually work out in your favor. Okay, so when you get in situations like this, do not hesitate to use this table, especially on your problem set. Now, I will say that on your quiz that's next week, I have a question very similar to the first one we did, where you shouldn't have to use your table. Okay, it's about the trend. Keep that in mind. So you already have the trend. You should already have the trend from last chapter. So you can use that on your quiz next week. Okay. Questions on this? I wore the wrong mask today. Now, well, when we talk about polar covalent bonds, and you have this unequal sharing of electrons, essentially, you have what's called a bond dipole that results, or a dipole moment. And this concept is what I have on your review sheet that has been crossed out. Okay. But I still talk about it. And so when we want to calculate the dipole moment, which allows us to determine which atom has a more negative charge and which atom has the more positive charge, and to what extent or what magnitude, what value. That's what calculating dipole moments does. And so it is produced by two equal but opposite charges separated by a distance r, and is calculated as the following. It is measured when you calculate it in dibiads. I always say it every year that way because it sounds what's the word I'm thinking of? Exotic. Dibiads. Anyway, As we just said, the greater the electronegativity difference, the more polar the bond is. And this is just what we would have done if we were to calculate the dipole moment. As you see, those are some really fun calculations. Not gonna lie. That's a blast. But again, the whole point of it is to allow us to see who carries a partial negative and a partial positive charge and what magnitude it is. But we don't worry ourselves with that. But what I am going to do over the next handful of slides or so is kind of give you some information that slightly contradicts a few things. Okay? So we're going to differentiate between ionic and covalent compounds. So we tend to expect compounds as molecules when covalent bonding is dominant. With properties of covalent bonds, we associate low melting points, low boiling points, non-electrolytic behavior. Whenever we have ionic bonding as a dominant process, we expect compounds to be brittle, but with high melting points and high electrolytic behavior in water. But there are exceptions. There's always exceptions when you get into the realm of atoms. Okay? So the ability to categorize if it's ionic or covalent does impart some insight into the properties of the substance. So how do we best do this? How do we best categorize something as covalent or ionic? And our simplest approach we've been doing is to assume that metal and nonmetal is ionic and nonmetal is covalent. But even when you do that, you still have exceptions. Okay? If we look at tin and chlorine, tin's a metal, chlorine's a nonmetal. We look at their compound that they form. Tin chloride is actually a molecular compound, even though it is a metal and nonmetal, because it is colorless liquid at room temperature. Ionic compounds are not liquids. It freezes at negative 33 degrees Celsius and boils at 114 degrees Celsius. Very low boiling point and a pretty warm freezing point. Again, not characteristics of ionic bonds. So, a more sophisticated approach is to use electronegativity. So if we think about the previous example of tin and chlorine, the electronegativity difference between tin and chlorine is actually a value of 1.2. The difference in their values. Sodium chloride, on the other hand, which has been confirmed to be an ionic substance, has an electronegativity difference of 2.1. So a pretty significant difference in terms of electronegativities. But I'm just knocking them out here. Even our sophisticated approach of electronegativity has one shortcoming. It does not take into account changes in bonding in association with oxidation states of metals, meaning their ionic charges. Another example is manganese and oxygen, which has a electronegativity difference of 2.0, which falls in the range of ionic bond. Anything with basically a 2.0 or larger difference is going to be ionic in nature. It is solid at room temperature. It does melt at 1,842 degrees Celsius and does have a crystal structure. All prime examples of an ionic compound. However, manganese can form an oxidation state of +7 charge. So manganese 7 oxide is a green liquid that freezes at 5.9 degrees Celsius. That's pretty warm to freeze. So this one does not conform to ionic compounds. So what they're trying to say is when oxidation states of metal increases, so does a degree of covalent bonding. Because when you get so high in terms of your oxidation number, meaning you've lost so many electrons, you almost feel like you might need to gain some back in some way or shape or form. So basically, a rule of thumb is when the oxidation state is highly positive, and this is, again, roughly speaking, a +4 or more, we should expect significant covalency or covalent bonding. So metals in high oxidation states, we find molecular substances like manganese 7 oxide or polyatomic ions like permanganate and chromate. So, as I told in another class, as we kind of further our journey in this book, which we're kind of limited by time at this point, we begin to find slight discrepancies or slight tweaks to our previous knowledge. This book does a great job of building up on previous material. So before these last few slides, we always assumed that ionic compounds were metal, non-metal, and non-metal compounds were covalent. But as I did more investigating and they saw the properties of certain compounds that were not conforming to those of ionic substances, they had to look somewhere else. And that other place was their oxidation states or their charges as ions. So we can and do have metal and non-metal substances, compounds, that are bonded together that are essentially more covalent in their characteristics than they are in ionic. So just a little piece of information there. That brings us to Lewis structures, which we are going to worry about after our quiz. Okay? That wraps up our discussion on 8.4.